You know, it's kind of hard to think of anyone who hasn't been touched by cancer in some way.
Yeah.
It's one of those things, it feels almost impossible to really wrap your head around,
Mm.
let alone, actually defeat. But what if I told you that one of the most powerful tools in this fight could be something you might not expect? Math. We're going deep today
Okay.
into the world of computational biology
Very cool.
with Francisca McCord.
Yes.
And she is using mathematical models to understand how cancer works, how it evolves, and how we can target it more effectively. So to kick things off, can you give us a clear picture of what cancer actually is at a cellular level?
Yeah. So cancer cells are essentially rule breakers.
Okay.
So unlike normal cells, which follow a very strict code of conduct, cancer cells just multiply uncontrollably. They invade surrounding tissues and they ignore all the stop signs.
Mhm.
So it's like a neighborhood where houses just start popping up wherever they please and disrupt the whole system.
And that disruption, I mean, that gets even more complicated with metastasis, right? That's when it really starts to spread and becomes so much harder to treat.
Exactly. And what makes it even trickier is that these cancer cells, they are constantly evolving within a patient's body. Think of it like this, like bacteria.
Okay.
Bacteria can become resistant to antibiotics over time, right?
Right.
And in a similar way, these cancer cells are always changing, adapting to their environment and becoming more and more difficult to target with our traditional treatments.
So it's not just like one disease, it's constantly shifting, almost like it's outsmarting us as we try to fight it.
In a way, yes.
Wow.
It's like, you're trying to hit a moving target that keeps changing its speed and direction.
Right.
So understanding this evolution, this constant adaptation, is absolutely crucial to developing treatments that are actually going to work.
Okay, so we've established cancer is complex, it's constantly changing. This is where I'm really curious. How does math even begin to help us tackle something like this?
Yeah, so math gives us this power to create models, okay, like simulations of incredibly complex systems.
Hmm.
And the human body, especially when it's battling cancer, is about as complex as it gets.
Oh, yeah.
So,
We're talking about using math to make sense of all of that complexity.
exactly.
Wow.
Imagine, like, trying to test every single possible combination of cancer drugs, dosages, treatment schedules in the real world.
Right.
That would be virtually impossible,
Yeah.
not to mention ethically questionable.
Right, of course.
So mathematical models allow us to do this virtually,
Okay.
using real data to see which approaches actually have the highest probability of success.
So instead of relying on trial and error in the real world with real patients, we can use math to run like millions of simulations and see what works best.
Yes.
That's incredible. That's incredibly powerful.
It is incredibly powerful. And the exciting part is that we're already seeing real-world results from this approach.
Wow.
So, for example, my team has been using mathematical models to develop personalized radiation schedules for patients with glioblastoma.
Glioblastoma, and that's a very aggressive type of brain cancer, right?
Yes. Yeah, and it's notoriously difficult to treat.
Yeah.
But by using math to model the tumor's growth and its response to radiation,
Yeah.
we were able to design a completely new treatment schedule.
Okay, hold on. This is where it gets really interesting for me. You're saying you used math to figure out not just how much radiation to give, but when to give it.
Exactly.
Wow.
Our models predicted that giving radiation 3 times a day,
Okay.
which is unusual,
Yeah.
would be far more effective than the typical once-a-day approach, and the early results from our trials suggest that we were right.
Wow.
The way the tumors responded, their recurrence patterns, it was all different.
So you're actually changing the way the cancer evolves by hitting it with radiation at these very specific intervals.
That's the idea. We're essentially using math to outmaneuver the cancer, to anticipate its next move, and counter it.
Wow, that's incredible. It seems like this kind of modeling could revolutionize how we approach cancer treatment on a much larger scale.
It has that potential. We're still in the early stages, but the possibilities are vast.
Yeah.
Just imagine being able to use these models to predict which patients might benefit from certain therapies, or to develop entirely new treatments tailored to an individual's unique cancer.
It's like taking a disease that's felt so random and unpredictable and turning it into something we can actually reason with, strategize against.
That's a great way to put it, and it's not just about treatment either. Early detection is another area where math is playing a crucial role. You see, if we can find cancer early, before it has a chance to spread and evolve, our chances of successfully treating it skyrocket.
Absolutely. Early detection is always key. But how is math helping us find cancer sooner?
We're now using mathematical models and machine learning to analyze blood samples for tiny trace amounts of cancer DNA that would have been impossible to detect before.
So we're talking about finding cancer through a simple blood test before it even shows up on scans or anything.
That's the power of these techniques. They're like incredibly sensitive detectives searching for the tiniest clues that cancer might be lurking. It's like finding the proverbial needle in the haystack, but in this case, finding it before the haystack even catches fire.
This is seriously mind-blowing. So instead of reacting to cancer after it's taken root, we're moving towards a future where we might be able to stop it in its tracks.
Exactly. Imagine a world where we can identify individuals who are at higher risk because of specific cellular changes. We could monitor them closely and potentially intervene even before a tumor has a chance to form.
So we're not just talking about treating cancer better, we're talking about preventing it altogether.
That's the ultimate goal. And with these advancements in computational biology, it's becoming more and more realistic.
This has been an incredible deep dive. So before we wrap up, let's bring it all back to our listener. What are the key takeaways here?
Well, I think the most important thing to remember is that we're no longer just throwing treatments at a disease and hoping for the best. Math is allowing us to understand cancer at a whole new level, to predict its behavior, and to develop far more targeted and effective therapies.
It's like we've gone from fighting in the dark to having a clear map of the battlefield.
That's a great analogy. And that map is only going to get more detailed and precise as our models improve.
So for anyone listening who might be feeling overwhelmed by a cancer diagnosis or just curious about the future of this field, what would you say?
I would say there is tremendous hope on the horizon. We're making incredible strides, not just in treating cancer, but in understanding it, preventing it, and maybe even someday making it a disease we no longer fear.
It's a powerful thought to end on. Thanks for taking us on this deep dive today.
Thank you. It was my pleasure.